Now you can get these cells without the protection circuits, and in fact, to keep this same form factor and include that protection circuit, it costs you a little bit of space. So sometimes you're giving up your capacity by having that protection circuit. I always try to use protected cells. Not that I've ever had an issue, and that's important to note. I've been doing this a while. I've never had an issue with venting cells or anything like that, even in the few unprotected cells that I use. But I still always go for the protected cells because I just kind of want that peace of mind. A lot of times in high quality current regulated lights, you're using a light that maybe has its own low discharge protection circuit, and it will cut off power to the light once it detects that the overall battery voltage has dropped below a certain threshold. So sometimes when you're using a light that has an over discharge protection like that, and you're using a cell that's protected, you've got kind of that double layer of security. Again, the thing you'll always hear from guys who've been doing this a long time is don't rely on your protection circuits. Keep track of what your battery voltage is as you're using it, as you start using your light, etc. And this is a really good time to introduce the idea of using a multimeter, a voltmeter. So this is just a cheap Radio Shack multimeter. There are much better ones on the market. There are a few that are even cheaper than this. The advantage to a really high-end multimeter is that you can test really high range of voltage and amperage. Also, you can record things. You see a lot of reviews, like Self-Built, that review flashlights online. They'll actually track the voltage over long periods of time. They can do reporting and stuff. You're not going to do anything like that with a cheap Radio Shack multimeter, but you'll be able to test your cells to see what the voltage is. You'll be able to test the current, which is nice to know how much light how much current your light's pulling off some cells, etc. So, highly recommend going and get yourself a multimeter like this. It makes you a much better flashlight owner because you can kind of care for your cells, care for your light, and you're not operating outside of any of the manufacturer's prescribed parameters. Anyway, sorry, we'll get back to that. You'll see us use that a little bit later here. But back to these lithium-ion cells. This is one of the things that caused a lot of confusion about the lithium ions is the designation, kind of the terminology we use for the sizes. Everybody's really comfortable with AAA, AA, C, D, kind of the typical old alkaline designations, but these lithium-ion cells use a different designation. The first two digits in the number refer to the diameter of the cell. This is an 18650, so 18 refers to the diameter. It's 18 millimeters across. The second two digits are the length, 6.5. This is a 65 millimeter long cell, so 18 millimeter diameter, 65 millimeter length. I honestly don't know what the 0 is for. I suspect it has to do with the chemistry. 0 maybe indicating that it's a lithium cobalt oxide. I'm sure somebody will correct me if that's not the case, but we can do the same exercise here with this other cell. This is I think they call it a 16340, so it'll be a 16 millimeter diameter and a 34 millimeter length, and again with that extra 0 there. But both of these, the significant difference is that, whereas with the alkaline cell and the lithium primary you're talking about, or the AA lithium primary, you're talking about 1.5 volts. The NIMPH cell, you're talking about 1.2 volts. With these lithium-ion cells, you're talking about 3.7 volts nominal voltage, and they recommend you don't overcharge them beyond 4.2 volts. So your voltage is much higher with a single cell, and that's where we run into a lot of issues when you talk about putting multiple lithium-ion batteries in series, which is end-to-end like this. You get some really high voltages. Sometimes the driver on your light won't appreciate all that extra voltage. So that brings me to a good point. Let me talk about that real quick. Here's another example. So here I've got a little 10440 lithium ion. I've even got a 10180, which is a little itty bitty cell. This is I think it's called a 1/3 AAA size, just to give you an idea, but those are used in some of these really small, like neck, jewelry lights and things like that. But the current that you can draw off these lights is limited by their capacity. The maximum discharge capacity for all of these lights have a maximum discharge capacity in the sense that the performance of the light starts to dwindle rapidly when you exceed the amount of current you're trying to pull from them. The one thing to be wary of, though, is that with these lithium-ion cells, unlike some of the others, you you run the risk of increasing that internal temperature to the point where you get, the venting action. And that is relative in part to the size of the cell. So for example, I could draw a lot more current from an 18650 cell like this than I could from this little 10440. The amount of current can be roughly correlated to the size of the capacity of the battery. So this is a 2600 milliamp hour or 2.6 amp hour cell. The recommended maximum discharge for these cells is 1C. That's 1 times the capacity, or the capacity in amps. So if this is a 2600 milliamp hour cell or 2.6 amp hour, the maximum prescribed discharge rate is 2.6 amps. Now you can exceed that relatively safely, I think. Sometimes we push these a little bit harder than that, all the way up to maybe 3 amps, which is near 2C. And what you always hear is that the disadvantage is that it reduces the number of cycles of kind of lifetime you get on your cell. If you're constantly draining the cell at too high a current, you reduce the overall number of recharges that you'll get out of the cell. You're damaging it for the long term, basically. But some people that's worth it to be able to make 1,000 lumens off a single 18650 and some of these really high end, high current P60 lights, with the XMLs and the SST90 LEDs. You're going to need to push the cell pretty hard. Some of these other cells, you're just not going to be able to get that kind of current. It's not that it's not safe to draw the current from these other cells, but you just won't be able to do it. You're not going to be able to take a couple of alkaline AA cells, put them in series, even if you put 3 or 4 of them in series and add up to the voltage of one of these lithium ion cells, you're never going to be able to draw the same amount of current. The chemistry just won't allow it. For really high drain applications, there are another lithium ion cell that is a different chemistry. It's lithium manganese. Typically those cells are called IMR cells. Couldn't tell you why that is. I'm sure Battery University could tell you. But these IMR cells come in some of the same sizes as the lithium cobalt oxide batteries do, but they have a discharge rate much closer to 10C, 10 times the capacity. So if you have a 2.6 amp hour like this, then you're looking at 26 amps you can draw off the light. Now, there are disadvantages. The disadvantage to that particular chemistry is that because of the safety factor, they've had to change the chemistry up a little bit, and you don't get the same specific energy. In other words, you can't hold as much capacity in the same size cell, so you lose some capacity. There are IMR 18650s, there are IMR 16340s. The other version, the AA version of this cell, I don't have any with me, I apologize, but the AA version of the lithium cobalt oxide cell is a 14500, 14500. That's the numeric designation for a AA replacement sized cell, and those do come protected as well. But anyway, yeah, IMR cells, if you want to run something like a better example here. If you want to run a P60 light like this Malkov or this Solar Force, and you want to put an over-ready triple in there that is drawing 5 or 6 amps or something like that, you don't want to try to do that off a single lithium cobalt oxide cell. You want to get an IMR cell. The capacity will be much reduced. Your runtime goes way down when you do that, but it's really the only safe way to do that. You won't see protection circuits built into the IMR cells, mainly because they don't need them, mainly because they don't expect you to exceed their capacity. And I think that because of that change in the chemistry, the thermal runaway temperature, I think, is 250 degrees or something. It's much, much higher than it is with the lithium cobalt oxide. So you won't need to worry about them venting under kind of normal use conditions. I have some lights, and I've got one of them here. This is a custom light that was built by a guy named Kevin, who owns a flashlight company called Lambda Lights. I don't know if you can see it, but it's got a big SST90 LED in there, and it's bonded directly to a big copper slug. And he's got some aluminum fins in here for more heat sinking. The whole idea is just to pull the heat away from the LED. The reason is he's got this thing driven really hard. I think, I don't remember off the top of my head. I think it's something where 12, 13, or 14 amps that thing is pulling. Now, that exceeds the ability of any of my lithium ion cells to handle that amount of current. So what we use instead are these big NIMF cells, these C and D NIMF cells. Now, again, you can really get a lot of current out of these NIMFs. They will allow you to draw about as much current as you can. Now, there are some cheaper cells, there's some more expensive cells. Some people that have done tests on these suggest that, these Tenergy premiums and some other high-end cells, the Centuras and some other brands that I'm not familiar with, you can get a higher current draw just by switching out your batteries, which translates to a higher brightness, higher overall output in your light. So, I purchased these batteries, although they're very expensive relative to a much cheaper NIMF D or C cell. Purchased these so that I could kind of squeeze the maximum amount of performance out of that light. But that light's making around 2,000 lumens, and it's really a thrower. I mean, it throws, I think it's 150,000 lux. And some of the guys that ordered I actually have a neutral LED in that one. Some of the guys that have a whiter LED will throw even further. So big time high power light requires you to get big time high power cells. So that's why I have these out here. The other mag I have over here is actually just has a Malkov drop-in in it. I've modified that from the stock XPG LED to the new XPG2 LED. So a little bit different LED, but the driver circuit that's in there is the same stock circuit. It's probably drawing 1.2 amps. Now I run these D NIMFs in there just because I can recharge them, but I don't need to. I could easily run that light on just a regular D alkaline cell, and it's not going to draw too much current for these. They might sag a little bit under load, but not so much that I couldn't use them. I keep using that term sag, and what I mean is the voltage sag, and I wanted to try to demonstrate that a little bit. I've got just a Malkov XPG drop-in inside of this this MD2 here. I want to take, I'm going to show you, I've got this Delrin insert, which is actually not made for this light, but it'll work for our purposes. So I'm going to drop it in there, and I'm going to take 2 of my alkaline cells, and I'm going to put them in the sleeve first, measure the voltage so you can see what the voltage is. Put my voltmeter on, and you're not going to be able to see the readout on the voltmeter, you're just going to have to trust me here. But I'm reading about 3.23 volts for these 2 AA's in series. So I'm going to stick them then in the light, and this light is set to the high mode. When it comes on, it'll be, I think it's usually drawing about 1.2 amps. So we'll measure the voltage under load and see what that change was. So now I'm reading 2.88 volts. So you'll see that just by turning the light on, oh sorry, you probably couldn't see what I was doing there, but I'm actually, the light is actually running. It's just it's just hard to see on the camera here. But when the cells are powering the light, the current that the LED and the driver are pulling out of the cells, it causes the voltage to sag. So from 3.23 volts down to about 2.8 volts. So when I talk about voltage sag for various cells, now you kind of know what I mean. If I were to put the lithium cells in there, you'd notice that they wouldn't sag quite as much. If I were to put the NIMF cells in there, they wouldn't sag quite as much. They just perform a little bit better under load. So sorry, I wanted to do that little demo so you could see what I mean. Anyway, I think the next kind of thing to talk about are the various configurations that you can run these cells in. Now you know a little bit about the voltage that each of them has, you know a little bit about what kind of current we can draw from these various cells. I want to talk about how that comes into play practically for using in flashlights. So we'll do that in the next part here.